let's start with our lecture. So, thermal diffuse scattering. If you use that on Google Colab, we install pyTEM lib, which we don't really need a lot in this case, but we use ABTM, so ab initio TEM. It's a nice Python package that makes it available to do a simulation of convergent beam pattern. And since a high-angular dark field or any of these scanned images are basically, you scan the image, you simulate a diffraction pattern, and this diffraction pattern you take now, you integrate over certain regions, and that gives you the contrasts that you're looking for, right? So that's the idea behind it. If you take only the zero beam, that is a bright field image. If you take any of the outer ones, it's a dark field image, and it's annular because you do it integrate over a ring, okay? So all we need to do is we have to simulate a diffraction pattern. We load, or we not load, we load our different packages, and you have to make sure that this ABTM is installed. And now we talk about dynamic diffraction. So as I said before, we can actually have several diffraction events in there. So we are not longer in the kinematic scattering regime where we have only one scattering event. So that is what makes X-ray scattering and neutron scattering easier to use, since they don't have that. Actually, they're trying to get to that with neutron scattering because they realize there's a whole lot of additional information in there. And as I said before, it can happen on a single atom, which atom is very strong, so you can actually have double scattering already on a single atom. The basis for all of that is the CBED theory, which is based on the Schrödinger equation. Our usual Schrödinger equations here. We don't go too much into that. The total energy is, of course, the total energy of the electron. So that is our acceleration voltage. We use it in the wave picture. So we have a wave function. And we have the kinetic energy. Again, that's the boring part. That is just the energy. And then the potential energy, that is our crystal. So that's, this interaction is what we are after. The charge of the electron is clear, so we have a Coulomb interaction. And we have this Coulomb potential that we scatter at is positive. So we always have to think about what are we really scattering at. So with X-rays, with photons, we scatter at electron density. With electrons, okay. It's not working very well today, huh? If I put it closer, okay. So, I knocked it out, okay. So, the crystal potential is positive, so there is the positive nucleus that is screened by the electrons around it. So we're not seeing the full positive nucleus, so we see the one that is screened and reduced by the electron cloud going around that. The interaction potential, funny enough, is very close to the Bohr radius, so about half an angstrom. In order to solve this Schrödinger equation, Bethe made this trick with the Bloch waves. So he said, hey, there is a periodic crystal. My solution also should be periodic. So that is the periodic Bloch waves. Because they are periodic, we can make Fourier expansions or Fourier series of that. So we have a whole bunch of periodic functions, and we are looking at their Fourier coefficients. Turns out that we have these Fourier coefficients are for each of the diffraction spots. And so basically we have in each direction running two Bloch waves. One is on the atomic columns and one in between. And so if we are looking in a high-angular dark field detector, on the atomic column it's bright because we scatter a lot. We'll come to that in a moment. And in between of them it's dark. So in a way, what we do is a near-field technique where we select the one Bloch wave over the other Bloch waves. So that's what we are trying to do here. Then with this periodicity, so symmetry and quantum mechanics is very, very close. So we are using that. And with the usual substitutions that we do, we are arriving at this equation where we effectively separated everything in terms of our Bragg angles and Bragg reflections. And there is a second term that shows up in this equation. Not sure where we have that. So this is just the first term here. How can I? Nah, okay, sorry. Okay, so we have this first term, and that is just the boring Bragg reflections. And we have a second term here. And that depends now on the interactions between the different Bragg reflections. And it turns out that there are a whole bunch of quantum oscillators. Okay, quantum oscillators. So if, and that it was the beauty of the two-beam conditions. So what you try to do is you go into the exact Bragg condition. Okay, we know now, we tilt, right? The Ewald sphere hits only two of these Bragg spots. And then we have two strongly excited beams. And when we hit the surface of our sample, of course, we have only the zero beam, and that is strongly excited. It's a pendulum. It's an oscillator, so it's strongly excited. As we go through the sample, it looks like we have two pendula. What is it? Pendulums? Huh? Pendula. Okay, I did it right the first time and screwed up the second. That's good. So we have the first one going on, and so if this one is connected, and in our simple picture with just a spring, right? Then at some point, the second one starts being activated, so we get diffraction. And funny enough, at some point, all the intensity is in the second pendulum, so our diffracted beam, and then it gives it back. So with two pendulars, I can do that with my hands, right? with 3, I need more people. And it turns out mathematically 3 can no longer be calculated effectively. So that's why the 2-beam condition was so popular and dominant before we had fast computers, right? So in the 60s and 70s, especially, it moves off or what? I don't know. Okay. So especially when my supervisor, when I was a PhD student, so he was a lot into these 2-beam conditions. And you can imagine what I did in my TEM class. We calculated that backwards and forward. So nowadays we use a different method actually than trying to solve that. And we are trying to do that for many beams. And for each beam now, the more beams we have, the larger of a matrix we have with complex numbers, right? Because we need 2 solutions for our Bragg reflections. So this Fourier series is based on complex numbers. So what we do in a multislice technique, that is based on the Howie-Wieland equation. R.G. Howie, so he was in the Cavendish lab, interesting person. Wieland was his postdoc, I think. And so the multislice is relative straightforward. And we can do that with the diffraction that we already introduced in the first lecture. So if I do that here, we have our crystal. It didn't show. I have my plot. This, okay, I'm in the. Okay, here's my plot. So we have a unit cell, and the single unit cell, I'm saying that now so that I don't forget that, is not enough. You can imagine we are wanting to do that going backwards and forwards between real space and Fourier space. So we always have to have relative large unit cells so that we have a good resolution in reciprocal space, because the width was the width or the dimensions of our object in reciprocal gives us the resolution. So the larger that is, the better of a resolved diffraction pattern we'll have. So we have here strontium titanate. The strontium sits on the corners of this cube. Somehow it's distorted here. Wasn't that the case before? We have titanium sitting in the center of that cube. And the oxygen sit on the faces, okay? And what we do is we now make slices even of this unit cell. So we have one slice in the titanium oxygen plane, that is the orange one, or the strontium oxygen one, that is the blue one. Now what we have is we have the slices are so thin that we can handle them kinematically, right? So as long as we are not trying to do uranium oxide, we should be fine. So we do something, we create very, very thin slices that are kinematically okay. So we can do kinematically. So we hit with our electrons that sample, and we hit it at the first layer here, and it scatters. And that's what we did in our first lecture, right? So we did the Ewald sphere, blah, blah, blah. So we get our Bragg reflections. what we do next is we calculate the different path lengths because they all come with different angles, right? So the electrons that hit the second one, we have to first scatter, and then we have to translate them. So that is now where the problem comes in. Diffraction we did in reciprocal space. The path length is obviously in real space. So we go reciprocal space, path length, real space, then we scatter again, reciprocal space. So we do a lot of Fourier transforms as we go through that, and we do that for each layer. So we have a scattering part and the transport part. In my class, we did that. You know, you can actually do that. The formulas are out there, so you can check that out if you want to. So we can do the same thing in ASE, the atomic simulation. And you see, okay, maybe the mouse is better. So this is our strontium titanate. We have the different layers here. And that is what we want to do. So we have X and Y direction relatively small, and then we have a relatively thick sample location. The X and Y direction gives us the resolution in Fourier space, and the depth gives us the depth dependence of what's going on. We saw our pendula swing backwards and forwards. So which one is the last one, right? That's what we want to find out. And there are lots of them, and they're all interconnected, and it's and we can do that by looking at that. So, okay, we make this a bit better, and then we define a potential, and we calculate where are we here? So we do our multislice calculation, and we go through that sample that we just had. So it was a certain thickness, right? And we just ran that. So this is our what comes out of the sample. And now we mess it up with our lenses, right? So we make a spot diffraction pattern. So we come in with a single direction, so it's parallel illumination, and then we have our spot pattern. So the intensity now in the different spots is different because depending on the thickness, it's distributed out. And if it is not perfectly in zone axis, then you see that they are not distributed perfectly in the right orientation. So you can come in with a slight angle, and then you would have changes. The next question is, how do we do that now for convergent beam pattern? And okay, let's zoom out a little bit. Let's go back here. We don't see, say, Holtz rings, and so we'll see whether we don't see in this part any kind of evidence of our Kikuchi lines, and we should. So the question is, where do they come from? And that's where we get with the thermal diffuse scattering. So a large portion of our diffraction pattern comes actually from the electron interacting with the phonons in the sample. The atoms don't stand still, right? We know they are wiggling backwards and forwards. So the phonons are collective oscillations of the atoms, and even at 0 Kelvin, because the energy is well defined, the atoms cannot be placed at a specific point. So they wiggle at all points in time. And this oscillation of the atoms are actually a main contributor to our electron diffraction pattern. And the key factor here is the Debye-Waller factor. And so all of these atoms are deviation from the ideal position by a certain amount. In the average, they are, of course, at their position, or it's the ideal position. Oh, do I have things in the kinematic pattern? Well, kinematic pattern don't exist. Maybe I didn't check the okay. Pendulums. Pendular. Okay. What about the simulation of kinematic pattern? There is no kinematic pattern, more or less, in electron microscopy, except if you make it very, very thin. And so you can make a diffraction pattern of just 1 or 2 layers, and then we have the kinematic approximation, right? The kinematic approximation we did before, and there we have the same, we have the intensity of the diffraction spots according to the structure factor. We did that before. Now we are trying to integrate that and go further to include this dynamic diffraction. But it was a good point. So maybe I didn't make that very clear. So kinematic was a simple structure factor. Now we go backwards and forward. If it's very thin, it should be the same. So they wiggle around an ideal point. And so if you look at that in an image, they sit where they are supposed to be sitting, because you need many different electrons to determine a single atom position. Yesterday we saw we needed about 2,000, so it's about 100 per atom or so. So then you get a good definition of where they are sitting. So what we do is we make the so-called frozen phonon approximation. So what we do is we randomly wiggle the atoms and have 12 ensembles that we are using. Where are my atoms? No. So that should work better. Do we not have? Let's check it out. Okay. Here we are. I wasn't waiting long enough. That was the problem. Still doing things, I think. Okay. So we had it here for a second. Let's see whether it comes up here. So we have the ones that are sitting exactly where they are. If we are using the ensemble that is, the plotting routine is a new version of JupyterLab is not great. So let's double check here. We'll see how that average of the frozen phonons looks. Okay, here we are. So you see the oxygen now sits not longer exactly in the center, and everything is moving around and about a little bit. So the not sure why this. The strontium column are now not longer perfectly straight. What they really are is they are wavy going through that thing. And so we calculate now the diffraction pattern for 12 different ensembles where they are moved around and about. Okay, so that takes a little bit. On my computer, it should take a little bit less than 30 seconds. Okay, so we did that. And now, if my plotting routine works, and it doesn't, we'll do that. Okay. So we have a very different configuration, and now we can plot our diffraction patterns. I have to put a lot of plot shows in here nowadays, so okay, here we are. The symmetric ensemble, no indication of Kikuchi lines. A single thermal ensemble will already get you Kikuchi lines. So the Kikuchi lines, as we said, are based on the center of the microscope sample, and then are going into different orientation depending on the Bragg conditions that they will see. So here we see very clearly the different Kikuchi lines, and if we do that over 12, then that's a bit much. Then we see actually that they have already a symmetry part included, right? Okay, well, just we have a symmetry part included for fold. So again, we are in the 001 direction. So, and that comes purely from the symmetry of the Kikuchi line bands. So the more of those thermal ensembles you integrate, the better your Kikuchi lines will come out. Then let's do this one here. They cannot hurt. That's the same thing. And now we also see that it's not what I wanted to do. This is what I wanted to do. So here we see the Holz rings are showing up now as well. And again, they are a little bit more visible once you do that. In convergent beam, we do very similar conditions than what we had before. And we do what we did yesterday, when we tried to figure out in the Röntgengram how we get our beam shape. So all we do is we make an aperture that is all one, and everything outside is 0. And if we do now a Fourier transform into real space, then we have our probe position with all the different angles and the different intensities. And in an ensemble that is symmetric, so we use the same potential. We don't do anything different. We just use many more of those things. And we see, okay, we have our convergent beam pattern. We already have some amount of interesting features from our excitation error, but very, very primitive ones. So the dynamic one gives us actually more interesting pattern, because it is the dynamic diffractions that we also put into the into this excitation error shape that we use virtually. And then okay, let's check it out. That is new, sorry. I apparently did that when I tried it out, I did that in VS Code, which has a different one. And so here we see now how the center part is changing. We have some amount of structure in the center, and then the square of the squareness of the crystal symmetry, so is showing up here as well. But most importantly, now we also have our Kikuchi lines, and this is actually really how our diffraction patterns look like. So it's very similar to what we saw. Let's look at this one. I think I just want to look only at this one thing here. 45, a little bit time. So if we only plot this thermal ensemble now, zoomed out, plus. No. Okay. Still have no color bar here. How did I do that before? Oh, C-bar true. That's easy. So here we are. We have now our color bar, and I want to see apparently I don't have enough of my intensity to have, yeah, you see it weakly here. No, you don't see the Holz rings. Don't think we have it far out enough to see that. Anyway, so with this kind of simulations, you can directly compare that to what you have in the microscope. So we had silicon 100, and in the beginning we had the plan for the hackathon to do something simple and just make you do the same thing. Do the same thing as we do here with tungsten titanate with silicon and get you to the right thickness. But now we have a much more interesting one with 4D STEM that we are going to do as a hackathon. So, but you can imagine all we have to do is in the beginning, we have to do the silicon one, and then we can do the same notebook again. If you haven't done so, look at the ASE. It's really your friend if you do things with diffraction and simulation. All you have, all the different crystallography tools are included, and it's directly compatible with ABPM. It also gets you directly to things like density functional theory or molecular dynamics. All of those things, it will make your input files, and many of them run that. It's a very powerful tool, fully scriptable in Jupyter notebooks. So pyTEM lib is based on this ASE. So I get all my crystal tools from the ASE platform. Okay, so we have another 10 minutes. Do we have any? So we have some questions here. What's going on? Okay. Okay. There are some question and answers already. So just for the ones who don't follow that. So the seed is for the random generator. So we want to have set random, but sometimes you want to double check the same kind of ensemble. So you use the same seeds for the random number generators. So that's one way to ensure that. The concentric streaks in the Kikuchi diffraction pattern, and this that is down here. Concentric streaks. Actually, if you follow them all the way through, they are not concentric, they are actually just square pattern. So you can see where, and then, so it is a fourfold symmetry of the diffraction pattern. When the Kikuchi bands overlap, you will see them in all directions. Again, very, very sensitive to any kind of tilt or deformation, since that will redistribute. Yeah. So the pattern we saw in the EM. Actually, I had a notebook. I can probably post that later. And then we can do the silicon 110 in 10 minutes. Put on the spot, it's probably not directly possible, but you can actually see that, and I've done that. So for 200 kV, the patterns that we saw was about 80 nanometer, and then about 60 nanometer for the thin bits. So you can actually do thickness measurements within a few nanometer, and that would be the crystalline product. Obviously, we also use this kind of diffraction pattern for calibration. If you have a known sample, you know where the diffraction should go to, and so you can calibrate things. And that's what we're going to do after lunch. Maybe I can get the silicon one up and running, and then we do that one as well. Anyway, so the point is, this runs very fast and easy. If you want to have more, you just run it with a few more ensembles. And the larger your cell is, the higher is the position in the diffraction pattern, and the smaller the pixel size in real space is. So that is how far out you go in reciprocal space, right? So the pixel size in real space is the field of view in reciprocal space, and vice versa, the pixel size in reciprocal space is the field of view of, and so that is directly related to the resolution you get. In this case, it's for the inner part, it is certainly enough. If you're interested more into the Kikuchi pattern, then we have to look at that one. You can see into two different how the thermal ensemble changes things as you go out from the center here. So you have this weak oscillation, the weak reflections in the clean ensemble, and the intensity gets redistributed dramatically in the thermal ensemble. Okay, that's how far. Okay. Ah, yeah, super. In the audience here, sorry, I forgot you guys. Yeah. Okay, you didn't use your microphone, so I'm not sure whether the online people heard that. So the question was, can we differentiate the thermal diffuse scattering from the crystal structure itself, I guess, right? Yes, you can only do that when you do this with simulations. So that's the part where we really want to check it out. And they are actually mutually dependent, because the thermal diffuse scattering is part of the phonons, and phonon scattering is, of course, one way how we characterize them. So that's not independent. If you can make it actually, at least in ABTM, you can make it very, very sophisticated. So you can use potentials from a density functional theory. You can have that calculated, and then with molecular dynamics, you calculate the phonon dispersion, and then you can get that extremely close and see which kind of things contribute most, because you can switch it on and off in the computer, right? So that's the advantage of that. And that's what we do, right? What's very simple in this kind of convergent beam pattern is anything that is asymmetric. So if you look at antiphase boundaries of polar materials, you see immediately the diffraction pattern stays the same. So the location of the brackets stays where they are supposed to be, but the pattern inside the disks is changing and flipping or rotating depending on what kind of pattern we have. And if you have a simulation with that in your paper, you will have no questions from any referee. So any reviewer will just go along with it, because if we can do a simulation and we can show that it is agreeing in the relevant features, that is usually good enough. So there's different levels of sophistication where you can use it. No, excellent question. Thank you. Any other ones here? Can you use your microphones and I don't have to repeat it?
Okay. Hey, just quick question. Like, I did a simulation here, and I felt like the perfect ensemble, the symmetrical ensemble, doesn't look like have a push band like the thermal ensemble.
Yes, that's exactly the point. So the perfect. Okay, so that is exactly the point. The perfect ensemble cannot have Kikuchi lines, because the Kikuchi lines come. It actually has very weak ones. So if you do it much thicker, you'll find it a little bit. But the Kikuchi lines really come from an interaction of the electrons with the phone. So if you don't put it in, you don't get in. You're not getting it. You get a weird effect at some point. But the strengths of the Kikuchi lines can actually be quantitatively evaluated here.
So you can use a Kikuchi line to evaluate how much phonon you have.
Yes. So and that is sometimes done. So you're looking, you want to suppress the phonons and this kind of thing a little bit. And then you can go to liquid nitrogen temperatures, and you will see the effect. That you definitely will see the effect. And if you want to simulate that, then you just let them not wiggle as much. So you reduce the Bivalla factor, so the deviation from the ideal position, and then you can see how much that will influence that. So yeah. And if you heat it up, you see it even better. There is the melting point is your limit, right? As usual, you don't want that in the microscope. Okay, so we're at lunchtime. Any other questions? Okay. So yeah.
So for thermal ensemble, is there a number of the configurations that you use for solving phonon? For example, in the code we are using 12 like number of phonons to solve phonon approximately. So is there a fixed like optimum number that we could use for saving that, or?
It's an optimum number. Well, it's a how parallel, how much computer power you have after a certain point, it will not change much anymore. Right? So you just go for convergence. So 12 is the minimum, I would say. So I use that. But if you do 30 or 50, so if you do it on our supercomputer, so I usually get 48 nodes for my notebook. And then 48 is my magic number, right? So it depends on the number of CPUs and threads that you can do nicely. That is a nice thing if you use a well-maintained software package, so that runs in parallel and it's nice. Over lunch, What? Okay. Never mind. What I was doing with the same notebooks that we had before, if we check the part, so we did all the rest. So instead of strontium titanate, I just put in here silicon and said we'll put, this is not what we want, so this is not right. Yep. So if we do, say, crystal here, it's opposite of what what's going on, what you think. So this is our silicon crystal, and it is thick. How thick is it? 32 unit cells. It's not big enough. So I was making one with 160 unit cells. Get an output, thermal diffuse. Okay, and then I got my diffraction pattern, nicely square. We don't have enough resolution, obviously, in our diffraction patterns. We see that. Okay. But we see also we have now our Waltz rings that we observed in our microscope. To remind you, where were we? We were on the microscope. Takes this out. It's not quite in zone axis, right? You see that here. Let's take the High-Angle Dark Field out. Our camera lens is not good enough. We need a larger, smaller one. It will change our diffraction a little bit. And here is our Waltz ring. Okay. So we do the same thing as we do in, zoom in here some. So we have this square part in the center. Let's go to a thicker one. So this one is apparently much thicker than 60 nanometer, 80 nanometers that I had. And this one is thinner than that. So these two pieces, and you can just read that off from the intensity, from the number of oscillations in the zero disk, in this case. Okay. So it can be directly simulated. And of course, you need the thermal diffuse scattering to get to that point. So that is still strontium titanate, I think. Okay,